Virtual temperature. We're going to define a quantity known as virtual temperature because we're particularly interested in issues of density and buoyancy. And we find that the ordinary temperature just won't do. Let's derive the specific gas constant for moist air. And we can write that as the mass-weighted mean of the contributions of the different constituents in terms of their specific gas constants. So you can see the sum in the red box. R is equal to 1 on M multiplied by the sum of the Mi by the Ri, the individual gas species. So the specific gas constant of moist air is equal to mdRd plus mvrv on the total mass of the dry air and the vapour. And then you can break up the numerator into its two expressions. So if we then want to simplify this, we're going to firstly get rid of all expressions relating to the mass. So we divide through by the mass of the dry air, top and bottom. For the first expression, that gives us 1 on 1 plus R by Rd, and the second expression, R on 1 plus R by Rv. In an earlier video, we saw that the definition of the specific humidity, QV, was R on 1 plus R, so we can replace the R on 1 plus R in the second expression. And it's easy to show, given that definition, that 1 on 1 plus R is equal to 1 minus QV. So we've reduced our expression now for the specific gas constant for moist air to a term involving the gas constants for dry air, vapour, and the specific humidity. Let's simplify that further and get rid of any reference to the gas constant for vapour. So we'll leave the first term as 1 minus QV by Rd, and the second term we'll modify by multiplying top and bottom by Rd. Now Rd on Rv is the ratio epsilon, which we introduced earlier, which is also the ratio of the molecular weights of vapour to dry air. And so we can take out a common factor Rd, which is the middle term, and it's Rd multiplied by a term inside the brackets that involves the specific humidity. And the last term on that line is just another rearrangement, nothing new. Now, given the value that we know of epsilon, we can finally write that the specific gas constant for moist air is equal to the specific gas constant for dry air multiplied by a term involving the specific humidity. Does that make sense? Stop the video and have a think about that for a minute. So how did you go? Did you get what's wrong with that? We've calculated a specific gas constant, but it involves another gas constant and a variable, the specific humidity, which is a measure of the amount of water vapour in the atmosphere. So it's a bit inconvenient to have a variable constant. So instead, let's write out the ideal gas law for moist air, P equals rho RT, where the density is the combined density, and the mixing ratio R, as is written as before, Rd multiplied by 1.1 plus 0.608 QV. And so you can write the ideal gas law as shown in the box in red in the bottom. So instead then of having a specific gas constant for moist air, let's use the specific gas constant for dry air and multiply temperature by the expression involving the specific humidity and define that as the virtual temperature. So the virtual temperature is a function both of the ordinary temperature and the amount of water vapour as measured by the specific humidity, so that we can write the ideal gas law for moist air as P is approximately equal to rho Rd TV. So what's the implications of that? What does TV mean? Well, consider a dry parcel of air and a moist parcel of air, and they both have the same pressure and the same temperature. We can write out the ideal gas laws for both of those and equate them, and we find that the dry air will be denser than the moist air because we have this equality, rho dRd is equal to rho R, and the specific gas constant Rd is less than that for moist air. Now if you go back to the expression of specific gas constants, they're equal to the universal gas constant divided through by the molecular weight. And so the molecular weight of moist air must be less than that for dry air because of the presence of light water molecules. So now let's leave the moist air unchanged and take a parcel of air that's dry and heat it isobarically, that is at this constant pressure, until its density drops to be the same as the moist parcel. The temperature of the dry air is now the virtual temperature. So the virtual temperature is the temperature that a dry parcel of air has to be raised to until its density is the same as a parcel of moist air. So the virtual temperature is used whenever density needs to be known with some degree of accuracy, because it's not simply a measure of the temperature but also the amount of water vapor that's contained. And it allows the comparison between air parcels with differing amounts of vapor. And it's particularly useful when calculating things like buoyancy, which we'll see later on in the context of thunderstorms and a parameter known as CAPE, and things known as geopotential heights, which are the heights of particular surfaces. We can take the expression for virtual temperature and simplify it slightly. So the expression we derived before is TV is T plus multiplied by 1 plus 0.608 QV, and we can approximate QV by R, and we know that's accurate to within 4%. But R is measured in kilograms per kilogram in that case, and that's inconvenient on a SKU-T log P. So we'll measure R in grams per kilogram, but we need to divide through by 1,000. So we have that messy expression in the third line that TV is approximately equal to T outside of 1 plus 0.608 on 1,000 by R. Then we ask the question, what's the virtual temperature at 270 degrees Kelvin? And so it's a little bit of sleight of hand here, but then we write the virtual temperature is approximately equal to T plus 270 by 0.608 over 1,000 by R, which we can approximate nicely as TV is approximately equal to T plus R on 6, where R is in grams per kilogram. There's three plots on the left-hand side, and there's the exact solution, or the exact approximation we have at the top in blue, and the approximation, TV is approximately T plus R on 6, which is the magenta line. And you can see when the virtual temperature is when the temperature is 270 degrees, our two equations for virtual temperature are exactly the same. When the virtual temperature, or rather when the temperature is 300 degrees Kelvin, we see that the approximation slightly underdoes it by at most about a degree, and when the temperature is 250 degrees Kelvin, the approximation overdoes it by a small amount. You can see it's a fraction of a degree. So this is a pretty useful approximation, and we'll use it throughout the course. Whenever you want to calculate the virtual temperature, read the temperature off a SKU-T log P, read the mixing ratio and divide by 6 and add them. And you'll find that the difference between the virtual temperature and the temperature in most cases is often quite small.